Hello everyone, welcome to today's video. I am again back with a surgery of a model which has been sent by one of the subscribers. And if I can bring in the question which has been asked. So the question you can see has been asked is about a model of uniaxial testing. And I already have some videos on constructing a generalized uniaxial test simulation using one element and also multiple elements. And in this case, the user says, hello, Professor Amir, I am one who asked about uniaxial stress condition in the plate with hole. So I think there was a comment about that, and I replied to the subscriber about what could be done about in that case. So I have done the uniaxial stress condition in Z direction, and it works with the help of your video. So at least somebody is taking benefit of my videos. Now I want to try it in Y direction and later in X direction. But when I check, the stress values in other direction is not zero. And here I attach my Abacus input file. So thank you so much for your willingness to help. Okay, so this is the question that the subscriber has sent me an input file. So let's go through the input file together and see what can be done. So I have opened already the Abacus. To import any input file, you go to import model, and then this is the file which has been sent to me. Okay, first thing is, this model is a plate with a hole. I think it's a too small model, and if you pull in this, which is Y, and also in X direction, then definitely you will have a lot of stress concentrations, and those stress concentrations will start to expand as you load it, and obviously you will not have zero stresses on the free surfaces. Generally, in uniaxial cases, you will have those free surfaces which will have zero stresses because you're only pulling in one direction. So let's look at the boundary conditions. Firstly, the mesh is not optimized. I'm not really would recommend to use this kind of mesh. You need a very fine mesh in these kind of models. So you go to the loads and you can see there is some fixed boundary conditions, and then there's a boundary condition in Y direction. So the user firstly said that when they apply the same displacement in Z direction, it works, and this is natural because your hole is in this direction, so you're not pulling, you're pulling in the same direction as the longitudinal direction of this hole, and hence you don't get that kind of stress concentration, and that's why you will have free surfaces which will have zero stresses. But when you are pulling in this or that direction, then definitely you will have a stress concentration, and that will change everything. So let's look at the boundary condition and see what it looks like. So you see this surface is fixed in one direction, which is X direction. This is fine. Then there should be another surface which should be fixed in 3 direction. So this is 3 direction. And I think it's this surface here. So you see the Z direction is fixed, which is this direction here. And so I cancel that. And then there should be one with Y direction, and you see this is U2, and it's the bottom surface which is fixed in Y direction. So this is correct condition for uniaxial case. You need to fix each surface in one of the orthogonal directions, and then you will have one surface where you will apply a boundary condition, all loading, and the two surfaces should remain the same to really replicate or simulate the uniaxial test. Now if we look at this displacement boundary condition, so it's applied in Y direction. So now if you see this is pulled in this direction, which is Y direction, so you will have a stress concentration, and that will definitely end up with some stresses here because your stress concentration lines will be moving towards the boundary. To avoid this kind of thing, you might need to make a bigger model, because this seems like a representative of that plate most probably, because this hole is too big as compared to the plate itself right now. So you can make a bigger model, and if this hole is far away from these boundaries, then it should be able to give you zero stress values at the surfaces, which is the correct boundary condition, loading condition. So this is one of the ways you actually select your representative volume element size or a unit cell simulation model size if you're modeling a very small part of the whole thing. So if you have a big material component and you are only interested in a certain area, you need to select that small representative volume element in such a way that it should at least still have the similar response as the overall thing. So in this model, I think this is the reason why you are having the stress concentration. To get those zero stresses, you might have to increase the volume, the material around this hole, and you have to keep on increasing it until you are far away from the hole, so that the effect of this stress concentration is completely diminished, and that way you will be able to simulate it. So I think it was an easy surgery because I don't need to simulate anything, but just to go to show you what else is there, check everything is correct. Mesh, you definitely need a modification in that. Material property wise, it's an elastic material. Most probably it's in millimeters, so everything is in megapascals. Then plastic properties, which is ideal plastic, and there is a potential which has been used with these constants. Again, all are one. There are no other things stepwise. I think it's a static general step. With energium is off. So again, if it's a large deformation, it might be worth to turn it on. And yeah, rest is fine. I think we can't mesh it right now because it's already an input file which is already meshed. So if I just try to see how it runs, then I will just say uni y direction. So I normally go with the full precision all the time, and then I submit. We definitely need a mesh refinement and proper meshing around the void, in my opinion, or the hole. So let's monitor it and see if everything is going fine. Yep, input file processor was fine. There are some warning on distortions because your mesh is not optimized. They already have a very low aspect ratio, as I can see. So definitely there are some problem, and it's finished. So if we go back, and now if we run the thing, so you see it's a very large deformation. So you need definitely a non-linear geometric effect there. As you can see, the stresses are constant in this case, but I mean, in reality, if you're pulling in this direction, then S22 should be whatever value it has to go through, but S11 and other stresses should be approximately zero, not completely zero, but approximately zero. So there is always some numerical errors. So if you look at S22, then that's also pretty large. And then if you look at S33, then it's also pretty large. And that's why I think it's just because of the stress concentration and the element. You can see stresses are varying inside the element. So you need mesh refinement. And also if you increase the size of this model or material around this hole and then apply the same boundary condition, then you will reach to a point where you will see that these lateral stresses are almost zero, but around the void there will still be stresses which are finite, and hence you will see a finite value. But if you again plot the stress, for example, I think along this surface here, so you can do the QD and then probe value. So you see the stresses are still low, which is around 18 as compared to the others, but they are not zero. So it's like right now it's around 18. You can see similarly S22. So that's also high, very high. That should be high because you're pulling in two direction. And if you go to S11, then they should also be small, which is around 12. So they are small, but they're not zero because you still have the effect of these stress concentrations. So I hope this helps you understand what's happening here. So the one solution is you refine the mesh, obviously, to improve the results. Second is you increase this, if it's an RBE, then you increase this material around this hole, and you keep on increasing it until you reach to the zero stresses. And that way you should be able to ideally model or find the size of the RBE which is optimal for your model, where you're actually satisfying the conditions of your Uniaxial test. So I hope you find it useful. I hope you found it helpful. Any questions, you can always get back to me. Thank you and bye for now.